All right, in the last couple of videos, we built up a bunch of theory. We said that if we had a second order differential equation like this, it would correspond to a linear system like this. So not all the linear systems that we've studied so far correspond to first order systems, because we've got to have a 0 here and a 1 here. Okay. All right, and the connection between them, I've just summarized here. The numbers that show up here, the Q and the P that I've got here, are built out of the numbers that show up here, the A, B, and the C. Okay. So we determined that here, what we wanted to do is solve this characteristic equation. And if we could find solutions to this, then E to whatever the solution was times T was going to be a solution to this differential equation. And here, we wanted to solve the same characteristic equation. That would give us our eigenvalues. Once we had an eigenvalue, we'd find a corresponding eigenvector, and then E to the eigenvalue times T times the eigenvector would be a solution over here. Oh my goodness, all this crazy stuff. Okay, so I want to take a look now at the connection between the solutions that I get here and the solutions that I get here in the different cases. So we're going to take a look at case 1, where I have two distinct real roots. Could be positive, could be negative, could be 0, but there are two different roots that are going to work. So I'm going to say S could equal S1 or S could equal S2. So that's going to tell me that then I know that Y equals E to the S1t is a solution. We'll call that Y1. And Y2 equals E to the S2t is going to be a solution here. That makes me suspicious that I could build the general solution as an arbitrary linear combination of these two. But I haven't spent as much time working with systems like with equations like this as I have with systems like this, so I don't have these theories. Now it turns out there is a linearity principle for second order homogeneous linear differential equations of this type, so that an arbitrary linear combination of these will be a solution. But I haven't explicitly stated or proved that previously, and I have proved something over here. So let's take a look at what the general solution is here, because I'm just going to take advantage of the fact that the Y value that I'm solving for here is the same as the Y value that I'm solving for here. So if I know how to build the general solution here, that's going to tell me how to build the general solution here. So here, if there are two distinct real roots, I would have lambda could equal lambda 1, or lambda could equal lambda 2. Okay? So it's a difference in notation here. I'm calling the roots lambda 1 and lambda 2 when they're eigenvalues. I'm calling them S1 and S2 when they're just roots of this equation. But it's the same equation. So lambda 1 is going to be the same number as S1, and lambda 2 is the same number as S2. Okay. Let's just suppose that I've then got some corresponding eigenvectors. I'm going to call this one V1 with components V1, V2. I'm just going to call the corresponding eigenvector here W2. There isn't a W1, but that just allows me to call the components W1 and W2. So I can use W's here and V's here. But I'm using a subscript of 2 on the vector to say that it goes with lambda 2. So I know that over here, the general solution is going to be Y equals K copies of E to the lambda 1 times T times V1 plus C copies of E to the lambda 2 times W2, where K and C are just arbitrary real numbers. Okay. So what I want to do is just write that out component-wise so that I can then see what my Y is going to be. My Y without a bar over it, my Y. Okay. So I'm just going to translate this into component form. The vector y is yv, And we're saying that that's going to equal, this will be, remember V1 was just V1, V2, and W2 was W1, W2. Okay. So in the first component, so what I'm going to get from here is k copies of e to the lambda 1t times V1 and k copies of e to the lambda 1t times V2. That's just translating this solution into component form. I'm going to then add this solution to it, and I'm just combining them right now into one vector here. So that's going to give me c e to the lambda 2 times W2 plus c e to the lambda 2 times W1, c e to the lambda 2 times W2. Okay. So this is what my general solution is going to look like if I write it out in component form. Now, what that tells me then is what my general solution for y is. It tells me that y is k copies of, kv1 copies of e to the lambda 1 times t. All I did was combine the k and the v1, which are just my constants. Notice these are playing slightly different roles here. K is an arbitrary constant. V1 is representing a specific number. That's the first component of the eigenvector that I found. Okay. Plus CW1 e, whoops, I dropped a t there, e to the lambda 2 times t. Quickly, just jumping up here, I had initially written just lambda 2. I had dropped the t, and I'd done that in both places. I apologize. There should be t's in these exponents. Okay. So this is my general solution for y. Again, c here is representing an arbitrary number. W1 is a specific number. It's the first component of the eigenvector that I found for lambda 2. Okay. But if this is an arbitrary number and that's a specific number, that's just an arbitrary number. I could call that a. This is also just an arbitrary number. Oh, actually, you know what? Let's not call that a and b, because a and b were already used. Let's call that capital A and capital B. Okay. And remembering that lambda 1 and lambda 2 are the same numbers as S1 and S2, this tells me that my general solution here is going to be y equals a copies of e to the S1t plus b copies of e to the S2t. It's the same general solution, it's just a difference in notation. Very cool. So the theorem that we had here, the linearity principle that said I could take an arbitrary linear combination of my solutions and that would still be a solution, that translates now over to here, but we didn't have to prove it as a separate case. And we didn't have any theory over here about how do I know that I've gotten all solutions. I could very easily prove that this is a solution because I could just plug it in. How do I know that I have all solutions? Because we had a theorem, wasn't one that we proved, that was beyond the scope of this course, but we had a theorem here that said if we could come up with two linearly independent solutions to a system like this, every solution would be an arbitrary linear combination of them. Very, very cool stuff. Okay, so I now know that that's how I find the general solution in the case where I have two distinct real roots to my characteristic equation. So what I want to do is, we've had a lot of theory, let's just do an example. We spent a lot of time in the last section working with systems. So I'm just going to do an example of a second order differential equation here. So let's suppose that I had 2 copies of y double prime minus 3 copies of y prime minus 2 copies of y equals 0. Okay. So it's a lovely second order differential equation, and I can see by inspection it does not correspond to a harmonic oscillator because I've got some negative coefficients in there. But But I know that I want to solve the characteristic equation, which is just 2s squared minus 3s minus 2 equals 0. The second derivative gets replaced with s squared, the first derivative gets replaced with s, and the y gets replaced with 1. Okay, so I want to try to solve this. I am going to factor. Oh my goodness, algebra. This is so exciting. Okay, so I'm thinking I want a minus 2 here and a plus 1 here. Let's see if that works. 2s squared minus 4s plus s gives me minus 3s minus 2. Ah, it's beautiful. So either 2s plus 1 equals 0 or s minus 2 equals 0. S is equal to negative 1/2 or s is equal to 2. So I now know that my general solution is y is equal to a copies of e to the negative 1/2 t plus b copies of e to the 2t, where a and b represent arbitrary coefficients. And it doesn't matter what letters I use for them. I used capital A and B last time. You could use K and C. You could actually use lowercase a and b because we hadn't used them in this problem. We had used them to describe the generic situation, but in this case we had a very specific numbers, so I hadn't used any letters. So any letters that you want to use for those arbitrary coefficients are totally fine. And doesn't that make this easy? That's really cool. I like it. We'll be back for more.